at Amherst. Chemical Engineering, Polymer Science 757, Polymer Rheology, EHH, Winter Lecture 18A. One of the difficulties when working with gels is their low strength. We most likely break them, or it's very easy to break those gels. And we, of course, try to avoid that. So let's go the other way in the following experiments and just break gels. So how will this go about? If we, for instance, crosslink our material during shear, then the extent of reaction increases in time. And we would measure the stress during that time. So the conversion here goes from 0 to 1. And around the critical conversion, we would reach the gel time, the gel point. Now, the viscosity is going to increase. So we will have increasing stress levels due to that. Theoretically, it will diverge near the gel point or before the gel point. But in reality, we're going to break the gel. So the real curve really gives us a viscosity like that. There are technical applications where you would like to break the structure which develops during crosslinking. You could make, for instance, thermoplastic elastomers in that process. Crosslinking the material in a stirred tank, in a highly stirred tank, and you're breaking down your structure as fast as you make that structure chemically. And that would give you a very elastic material. So broken gels might have even technical applications. So if we stay here on the left side here, we could do well-defined breaking experiments by imposing a constant shear rate during the crosslinking, and then the stress will be growing, and near the gel point, there's a transition from liquid to solid, and the stress will grow very rapidly because that would be a solid behavior, while this is just the liquid behavior, just representing the increasing viscosity. So there's a rapid growth of the stress, and when we stop the flow, some of the strain will recover, so because it's an elastic body. It wouldn't recover to 0, so what I did here in this graph might be overdoing it. Alternatively, we could produce a well-defined experiment by imposing a constant stress on the sample, and we would measure the resulting flow here, the resulting strain as a function of time. As the degree of crosslinking increases, the material becomes more viscous, and the process slows down. So the curvature becomes lower and lower, and in the solid state, a constant stress would result in a constant strain, and that's it. Now, when you take off the stress, there would be a recovery going back to some previous shape. Now, if the reaction has been pushed beyond the gel point, then we have to overcome a critical stress level before flow is being induced, and that would be the breaking stress of the soft gel. If you imagine you're spreading Jell-O on your bun, doing breakfast, that's the type of stress you would have to overcome with your knife when you're spreading the material in that, say, food application. But we would be interested now in the characteristic stress for breaking, the stress which is needed for rupturing the material, and we would also be interested maybe in producing oriented network materials. We would introduce molecular orientation in the gel state during flow and lock that orientation in by a cross-linking reaction and have interesting materials. Another application where breaking of gels occurs is the extrusion of a cross-linking material through a pipe. And that's done conventionally. So a cross-linking material is going through this pipe. You have a velocity distribution, 0 velocity at the outer edge near the wall, and maximum velocity in the center. Now, the residence time is very short in the center because the velocity is so high. But near the wall, the residence time is infinite. So the material has a long time to cross-link, and it will cross-link beyond the gel point, so it will build up a solid layer near the wall. As you do that, as you have this build-up, the active channel area is decreased. The shear rates in the center are increased because of that closing of the channel. So your pressure drop, overall pressure drop in the extrusion die or whatever that is, will be increasing during that process. And the stress level somewhere in the die will be high enough to break the material. See, there's one characteristic radius where the residence time is short enough so that you don't cross-link the material too much. It's a very soft gel still at that residence time. And then the stress level is large enough to break the system, and the further build-up of this layer will be prohibited. But as soon as you stop your process, you are done. You have to open the die and clean everything. So that would be interesting to model if we know more about the cross-linking systems during flow. Sundar Venkataraman did some specific experiments where he looked at the breaking of gels. And again, he used the conventional system which we had before, the PDMS, about 10,000 molecular weight, the 4-functional cross-linker, and the catalyst, the platinum catalyst, which is needed to have the reaction proceeding. He also could utilize that property of the system by stopping the samples. Here he would produce a small sample on a cone and plate, have the system reacting for some time, and then poison the catalyst. By diffusion, the system will be filled with that catalyst poison. All the catalysts there will be poisoned very quickly. The reaction is stopped, can be put in a rheometer, and then we could perform a dynamic mechanical test to see to look at the dynamic mechanical properties, and then see whether our sample, which we produced, is close to the gel point, whether it's a sol or gel or wherever it is in the evolution. So we would use rheology to characterize the system. And then we would start the real experiments after we would expose the material to a constant stress or constant shear rate and start breaking the material and then recover it. And again, small oscillatory shear might tell us whether we broke it far enough that we reversed the gel process. We might have, in this upper part, we might have produced a material which is solid already, but then breaking here makes it a liquid again, and then we can look at the liquid properties of the broken gel and study that in further detail. A dynamic mechanical experiment at increasing amplitude. Here measuring, in this case, we're plotting 10 delta, and also, I think, there was one other property. Now the stress amplitude here. Okay, we perform dynamic mechanical experiment at increasing strain amplitude, then the resulting stress amplitude is increasing. 10 delta is about constant, as we would expect it. It's not perfect, but it's pretty close. But that at some strain beyond 2, the sample breaks and 10 delta becomes more liquid-like. 10 delta is increasing, and the stress level is characteristic for the broken system. So a strain of 2, which is very small. We would expect for a soft material like a gel, we would expect a larger strain before breaking the material. But even that small strain is causing a rupture in that network structure. We can use that process now to reverse the cross-linking reaction. Here Sundar produced a material which has G' leveling off. It's a solid-like, and G double prime corresponding to that. So that would be the initial sample, and he would say for his shear history, for his breaking history, it would be gamma equal to 0. This is the initial structure. But then he imposed a shear strain of 14 shear units. He just took the sample and sheared it by 14 units. And then he checked, again, G prime, G double prime, and he found a material which is close to the gel type behavior. So he comes to the gel point now from the other side. And the statistics of that network at the gel point is completely different than the statistics during the original making of those gels. But then if he imposes a bigger strain of 63 shear units, he really goes back to this liquid state again. It's a liquid, and this is G prime, G double prime. So by imposing large strains, the material goes back into the liquid state. Last time we looked at the large strain behavior of gels and looked at the first normal stress difference and the viscosity of a material during startup of shear. Now, just to come back to this data, the shear stress increased in time, and the first normal stress difference increased in time. The ratio was proportional to time. That was the part which really was interesting in the constitutive equation, assuming that there's no rupture. But now we realize that beyond a certain strain, the network will rupture, shear stress goes down at that prescribed rate, and the first normal stress difference levels off, and everything is different. This would be the rheology of the broken gel, very, very complicated. But note that, again, around 2 shear units, the network is already breaking, and new rules apply to that case. Here's a set now of 4 samples which Sundar produced with increasing crosslink density. One sample was very close to the gel point. It's a little bit beyond. See, it doesn't follow power law directly. My stick is bent, so I want to show you a straight line here. So it's already leveling off, so it has an equilibrium modulus. And 2 and 3 and 4 are even cross-linked further beyond the gel point. Now, Sundar used this asymptote here as his characteristic value for extent of reaction, because that was experimentally available. So he has those 4 samples, and he started breaking them. A sample which is just cross-linked a little bit was breaking already in a shear stress of 50 Pascal. He imposed a shear stress over a period of time in a creep experiment. At 10 and 20 Pascal, the compliance was independent of that strain. So it's a linear viscoelastic material in this case. But when it goes to a higher stress, the material is less connected. Somehow it's getting softer, so it starts to break. And here the break is really accelerating. You could see that this behavior is suddenly changing. It probably breaks for a while, and then it becomes catastrophic. And if you wouldn't have stopped the flow, it would have ruptured completely. He looked at the same behavior at samples cross-linked further, and he realized that he needed higher stress levels to deviate from the linear viscoelastic range. This is the 3rd gel, and this is the fourth gel as he was breaking them. And then he plotted the stress level needed as a function of extent of reaction. Now, extent of reaction was really identified by the complex modulus at low frequency. He didn't have the asymptote itself, so he just took the value at the lowest frequency he could measure. And you can see with increasing G star, with increasing extent of reaction, the ruptured stress is increasing. The network's just getting tougher as you put more crosslinks in. So that's what he would expect. The scatter is tremendous because you're leaving continuum mechanics in that experiment. It's you're really breaking something. You're producing some wild response in the material and get some statistic errors to whatever you're doing. But the general tendency is, I think, understandable. The bonding energy has been reported in the literature. The bonding energy for our PDMS gels. This is the linear chain. This is the four-functional crosslinker. Now, after crosslinking, we would have a setup, something like this. We have CH2 chains and a connection between C and Si and Si and O. Now, the bonds are, the bond energies have been reported by Walsh. Between the C atoms here in a polyethylene type chain, it's 88 kilocalories per mole. And between the C and the Si, about the same amount of energy. But the Si-O bond here within the crosslinker has a much higher bond energy. So we most likely will not break that one. We most likely will break these types of bonds. We probably break the sample, we break the network at a different position than we formed it before. We will break it at the position where it is connected to the lowest bond energy. The making of the network really involved this type of bond, which seems to be more permanent. For breaking a gel, we don't need many bond breakages. We did some estimates, but it's very, very low. So I'm not sure whether we can even detect that. We would need a very sensitive spectroscopic method to see small changes in those bonds occurring during flow. But that's still on the agenda, something we would like to find out quantitatively. We would like to know what's happening during the breaking of those gels. This sums up what I wanted to report concerning the chemical gelation. So here I brought a summary of the different subjects which we discussed on the chemical gels. First, the gel point was characterized by a diverging largest molecular weight, largest cluster size, and with that, the longest relaxation time is diverging. So, see, the biggest molecule which still can relax is going to be of infinite size near the gel point. Therefore, it has an infinite relaxation time. The divergence of the longest relaxation time goes with the critical exponents S plus Z. Actually, this should be minus. Should be a minus sign up here. Minus S, minus Z. And that was an interesting result, which comes from purely experimental observations. There's no theory involved to derive that, except for symmetry, saying that in the approach to the gel point from both sides, you will be finding that. The relaxation spectrum is very simple near the gel point. It's given by a power law in time multiplied with some constant. And this spectrum holds between a lower limit, which at low molecular weight precursors is given by the glass transition, and in higher molecular weight precursors is given by the entanglement behavior, when we talk about tough gels. And the upper limit is really infinite. We're having the longest relaxation time diverging as discussed here. So it's important that this self-similar behavior occurs in the terminal zone. It's interesting that there's no characteristic time in the behavior. There's somehow correlation of relaxation phenomena over all length scales. The only characteristic time is the shorter limit, the cutoff at very, very short time. But otherwise, intrinsically, there's no characteristic time, and that's the fingerprint of the self-similar behavior, self-similar relaxation behavior. The parameters in that spectrum, if you look at the front factor S here, the parameters are given as a modulus, characteristic modulus for a group of networks and a characteristic shortest time. G0 is probably the modulus of the fully cross-linked system. If we take our system and make a perfect network out of that, that gives us about this modulus. And lambda 0 is the characteristic time of the precursor. Or if you take the ratio of this modulus and this shortest time, you have about the viscosity of the precursor, and that order of magnitude. N has been found to range over wide values, but there's no way of predicting the value of N. Percolation theory seems to give a value close to 0.7, and such high value of N, close to 1, has been found for gels from small molecular weight, low molecular weight, and for off-balance stoichiometry, and also when adding diluent to the system, basically when making soft gels. But as soon as we go to higher molecular weights, the fun factor is large, and N is going to be small in that system. And all of that seems to be very self-consistent when you look at experimental data, but the theoretical prediction is still missing. I didn't discuss theory of gelation, just had the purely theoretical approach, but I gave some references, or I will give you some references on percolation and scaling arguments or second-order transitions or molecular dynamics. It's an area of active work in the moment, but not in my group. We are looking at gelation in a purely experimental approach and talking to theoreticians to gain a more deep understanding of what we're seeing in the experiments. The chemical gels, as described above, behave very similar to physical gels. I will discuss that just after this slide, or starting to discuss that. So there's a great similarity, which I have to show. Applications of gelation are plainly for measuring the gel point itself. Understanding of the gelation phenomenon allows us to design new methods of measuring the gel point. That's very nice. We can develop new materials with interesting properties, having this information. And maybe we learn about processing during, near the gel point, processing during crosslinking. So that involves breaking of gels or all kinds of complicated phenomena. So that's it's wide open for further research. So far about chemical gelation. The question then is, what do physical gels do? Do they behave similarly? And we, as you know, we looked at physical gels also. So we would like to compare the rheology of physical and chemical gels in the following. And we would like to find the gel point of a physical gel. It's not well defined for a physical gel. In a chemical gel, you always can say the material before the gel point can be dissolved, and the material beyond the gel point is a gel. It cannot be dissolved anymore. It's just the big molecular clusters are permanent. In a physical gel, the connection between molecules is due to some physical interaction, and a solvent will dissolve that interaction. So the physical gel can be dissolved before the gel point and after the gel point. A solution test is not applicable. Therefore, it is very convenient to have a mechanical test, as we are having a rheological test, to find the gel point of those physical gels. So that's an interesting application we will be looking at. Let's look at a few features of the physical gels as compared to the chemical gels. The junction is very different. For the chemical gels, it was just a bond, very well defined. For the physical gels, we might have some ordered region, maybe some crystalline region, which has a lower mobility, which connects chains locally. It might be a local glass region. You might have a fluctuation in composition in your system, like in a block copolymer. You might have glassy styrene regions which cannot move at a certain temperature, and they connect a rubbery amorphous region and form a thermoplastic elastomer, form a network, and in this case the glassy regions are the connecting regions, they're forming the bond. Phase separation might cause gel, hydrogen bonding, and many different physical phenomena might give sufficient connectivity locally between chains that, so that the overall system behaves like a network. And the characteristics of that bond will give us, will determine the network behavior. For instance, the longest relaxation time is finite for a physical gel. This time is very long in crystalline systems, or in a glassy system for that region. But for hydrogen bond systems, this finite time is fairly short, and the system will behave a liquid when you look at that at times longer than this finite time. In the chemical bonded system, the relaxation time at the gel point was infinite. The time of the lifetime of the bonds is infinite, and certainly the gel behavior, this power law relaxation behavior, will go to infinite relaxation times. Here, for the physical gel, there might be a cutoff at lowest frequencies, or there's a finite time where it's been cut off because of the finite lifetime of those junctions. Something which hasn't been discussed and hasn't been analyzed in great detail. The functionality, the number of chains coming out of a crosslink, is well defined by the chemistry here. But in the physical gels, it is most likely not very well defined. If you have a large crystalline region, you have many chains coming out of every crystal. And then you might have a distribution of sizes of those crystals. So you have crosslinks which are of low functionality mixed with crosslinks of high functionality. The size of crystals, for instance, the size of those regions might grow in time. So the functionality is even time dependent in this case. The free variable in the chemical system was the extent of reaction. Here it will be the temperature, or if we go in a supercooled state where crystals are growing slowly, the time will be the parameter which gives us the changing extent of reaction. A nice feature for the researcher when working with physical gels is the reversibility of the bond. With the chemical networks, you have to produce new samples all the time, forever, whatever you're doing. But in physical gels, you just go beyond the gel point, and then you melt it again, and then you do your experiment as often as you want to perform that. It's nice that you can stop the reaction in a chemical gels and produce well-defined samples which you can test over wide temperature ranges, and you won't change the connectivity in those gels. So time temperature superposition is applicable, but due to the reversibility, we cannot do time temperature superposition in physical gels. So naturally, those systems will only be understood in very narrow windows, while here in chemical gelation, we will have data over wide temperature windows. You will see that's the characteristic of whatever we will be doing in this case. A typical experiment on physical gels goes something like this. We melt the sample. The sample would be partially crystallizable polymer. We go to temperature much above the melt temperature, and then at our starting time, t equals 0, we quench the sample below the melting temperature. It's a super cooled state, and crystals will start growing with time while we are holding the sample at a constant temperature. So the degree of crystallinity is going to grow. There will be some nucleation process and then some growth in most cases. So it's often very slow. In polyethylene, that's extremely fast because the chains can move into a lattice position very, very quickly. But for many polymers, it's a fairly slow process, and we can follow that process rheologically. We can measure G prime, G double prime. Starting at t equals 0, now we start with a liquid material. G double prime will grow, and G prime will grow even further, and the gel point will occur somewhere, most often beyond the crossover point. The crossover point is definitely not the gel point, except for a few exemptions, but we have to come back to this a little further in detail. The structure which we will get is something like this. A long linear chain, just to one molecule, schematically. That chain has some regions which are able to crystallize with other molecules. So those lines here belong then to neighboring molecules. So this chain will be connected here, 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 and here to other molecules. It might even form loops here, or it might form ties, flexible ties between two different cross-linking points. In the early development, these cross-linking points will be small. Most likely near the gel point, they will be still small. But then as time goes on, they will grow further. They will form some crystalline lamellae, which then interfere with each other and will form a network. So in the fully cross-linked system, you have a binary network, really. You have a network because flexible chains are connected by the crystals, very soft, rubbery network. And you also have a stiff network because those lamellar regions are contacting each other, and you have to break those first when you deform the material. So that breaking, this initial breaking, is a characteristic of those gels. I will come back to this with the second example. And the first example, I don't have mechanical properties. But historically, let's talk about the nice experiments of Klaas Teninhuis, who in 79, was it 79? Have to look at the literature. I think he did this earlier. He performed these experiments for his PhD thesis. So the data were already available, and he was nice enough to go back to his data, and he documented his results very nicely. That's a good example. That's what you should do when you do your experiments. You keep your data, so if anybody walks up to you in a meeting and says, how about your data 10 years ago? So how did this go? And he had those data available immediately and sent them to me. And I want to see whether these data follow the same evolution as we were used to see in chemically cross-linking systems. He had data of G star, also had data of G prime, G double prime, but let me pull out his original sheet on G star as a function of frequency. The early sample, in this case, well, should I? Yeah, let me come back to the schematic of the experiment again, what he did. He had a system which he melted at, I think, 160 degrees, and then he went below the melting temperature. It was 90 degrees, and then followed the evolution of G prime, G double prime during the aging process. And he found that after about 45 minutes, his sample underwent a liquid-solid transition. The polymer which he used was a PVC, and he plasticized this with DOP. And one of my slides here, I had the data. Yes, here I have some data. Here, this is the PVC from Solvay of a molecular weight of 240,000. He added a little bit of stabilizer, and then had DOP as a solvent. He had actually 90% DOP and 10% PVC for this sample. So everything was liquid in the beginning, and he cooled it down and observed the evolution of the mechanical properties in time. At a tenth of an hour, at 20% of an hour, he has this. At 40% of an hour, he has this evolution. And somewhere in this range, he claimed that the material went solid. By just by working with the sample, he realized that there must be some transition. He couldn't pin it down exactly, but when you work with a sample for a long time, you kind of know that. You don't need an instrument. You take a pencil, maybe poke in the sample, and you realize that this is undergoing a liquid-solid transition. But those were his original data. he gave me G prime, G double prime, and plotting 10 delta now as a function of, of aging time, we found that indeed 10 delta was independent of frequency at about 45 minutes. That's what what Klaas claimed was his gel point. Note that he didn't even take any data at the gel point. He took some data before the gel point and took some data after the gel point. But by connecting those lines, we know where the gel point is. We have a direct tool of measuring the gel point in this case. I thought this was amazing, looking at old data, not having checked them about these properties, and having such a neat crossover in this case. That was just fabulous. He never looked at the gel point, I said, and here when you look at 10 delta data now at various frequencies, you realize at 0.2 hours he was above, and at 1 hour he was beyond the gel point. And 0.4 he also would have been before the gel point. So he didn't have any data where 10 delta was completely flat. It doesn't matter because we know the type of evolution, and we can determine the gel point from this set of data. He also performed experiments with the same system by cooling down not to 90 degrees, but to 110 degrees. And then he followed the evolution of 10 delta, realized that 10 delta at different frequencies is going kind of parallels, approaching each other then, but then it's staying parallel. The material is always liquid. It never gels. And you can see that from the experiment immediately. You could stick your sample in the rheometer, and in 1 hour you know that this is never going to be gelling. You have to go to lower temperatures to do that. Or you go to a different solvent. The crystallization behavior depends on the plasticizer which had been added. Now he used a commercial plasticizer of Ciba-Geigy and found that at a higher temperature, at 110, the material crystallized nicely. The same polystyrene, also 10% polystyrene he used here. And it needed a little more than an hour to reach the gel point, but again, it's the same fingerprint. So the conclusions from revisiting Tinninhu's old data was that the same evolution of G prime, G double prime occurs near the gel point, the same as we saw in chemical gelation. And a new method now has been found for measuring the gel point for physical gels. People used maybe a sphere, drop the sphere on the gel and put the gel on the shelf for a week, and then looked at the sphere and saw whether it penetrated. Or some wild experiments have been proposed in the literature to see whether the materials are liquid or solid. Another person took a gelling system and put it on an inclined plate and coated a surface and had it running down a surface. And then as soon as the free surface of that liquid or this cross-linking material became ribbly, he said that's the instant of gelation. Somehow the molecular clusters became big in that system, and flow changes due to that. And that's probably a reasonable way of detecting the gel point. But it's very hard to be quantitative. Now here, it's a very simple test you can perform in a commercial rheometer. You just put in your sample and you see exactly where the gel point occurs. The finite lifetime of the junctions has not been a problem in our case because the crystals have such a long lifetime. The data, when you go back to them and look in careful, have only been taken in a small frequency window, was about 1 decade. So we really would like to know, is that power law behavior occurring over wider frequency ranges, and we should do some more. At that time, we got interesting polymers produced by Professor Chen here in the polymer science department. He changed the polymerization mechanism on a polypropylene so that he could produce long linear chains with alternating sequences. About 26% of the sequences were isotactic, and 74% of those sequences were atactic of this material, of this melt. In the molten state, the behavior is typical for a broadly distributed polymer melt. It's just a terminal zone and then entanglement region and glassy region. So nothing specific to be expected in the liquid state. So it's a good candidate to use the rheological testing to go through the gel point. If there would have been an abnormal behavior in the melt already, you would not be able to expect the gelation transition to be somewhat normal. So in this case, he had long linear chains with isotactic sequences and with atactic sequences. The isotactic sequences would crystallize, and the size would increase as the time goes on. And the long chain segments, which are atactic, would form amorphous region. The whole system is a thermoplastic elastomer, which has interesting properties. The mechanical properties of one of those systems, this is the polypropylene crystallized, polymerized at 25 degrees. We produced, Professor Chen and his group produced different systems at different temperatures. So this is the system at polymerized at 25 degrees, and with some small load, it deforms. Like here, the strain is something like with increasing strain, the stress grows, and then it somehow starts flowing. And then when taking off the strain, it goes back pretty much. It's very elastic, but some breaking has occurred. That's probably the longer lamellar region, the bigger crystals which are broken in the system. Since in the second experiment, when going to larger strains, the material is softer now, and you can break it further, and it still recovers, break it further. So eventually, you can really deform this material to very large strains, and here you have the evolving stress in that system. So it's a very nice thermoplastic elastomeric material, very, very useful. So for that sample, we would like to look at the gel transition. Let me have maybe break at this time and then proceed using rheology for characterizing this type of system, characterizing that type of physical gel. To get them in order. University of Massachusetts at Amherst. Chemical Engineering, Polymer Science, 757, Polymer Rheology, H.H. Winter, Lecture 18B. Let's look at the formation of the network of that polypropylene, which we just discussed. Our approach is the same one as before. We melt the structure, go to a very high temperature, and then quench below the crystallization temperature, stay in the supercooled state, and look at the evolving crystallinity. The first question would be, what's the melting temperature of that polypropylene? We take a sample, measure G prime, G double prime during a heating experiment. This would be a heating with 1 Kelvin per minute at a small amplitude oscillatory shear experiment at 1 radian per second. And you can see that the material softens drastically at about 65 degrees C. So let's call 65 degrees C our melting temperature in this experiment. We We will look at crystallization at 40 degrees C. The parameter will be the melting temperature or the temperature history. One sample will be just melted barely beyond the 65 degrees. So this is a pre-treatment with 75 degrees. This is highly melted at 100 degrees and very nicely melted at 150 degrees C. So that's our parameter for some of the data I'm going to show. So starting at time t equals 0, we measure the degree of crystallinity by annealing the sample and the supercooled state, and then quenching it even further and quickly transferring it to a DSC. And actually, in this case, this was done in a DSC. Sorry. So we perform this experiment, have the sample in the DSC for a while, and then start heating it and measure the enthalpy which we need for melting whatever crystal has been developed in the system. So with that experiment, we get the evolving degree of crystallinity in the sample for different preheating temperatures. We also measured G prime, G double prime in that sample here at 75 degrees. G prime and G double prime are growing as the degree of crystallinity increases. This is at 100 degrees C. The G prime, G double prime are growing. And then at 150 degrees preheating temperature, also the growth of G prime and G double prime. Note that at this frequency, which is 1 per second, 1 radian per second, G prime is always larger than G double prime. And this is because of the fairly high molecular weight, the high elasticity of the sample we will be looking at. So we have a sample which undergoes gelation. Gel point is somewhere here. But G prime, G double prime never cross each other. So for some people who still think that the crossing over of G prime, G double prime is the gel point, this causes a serious problem because they are never crossing. G prime, G double prime are never crossing in this frequency window. If we would have performed experiments at very low frequencies, we would have seen a crossing. But at this frequency, there's never a crossing of G prime, G double prime, and it gels anyway. So we should use another criterion for detecting the gel point. The criterion, as you know by now, is a spectrum of G prime, G double prime over wide frequency range. This is the initial sample, G prime and G double prime, measured initially. Then after 80 minutes, a power law region over 4 decades. It's fairly large. And then beyond that, at longer times, G prime levels off, and G double prime is of course, the viscous, more the lossy contribution. You can see that at a frequency of 1, here we are measuring here, and G prime is bigger than G double prime initially. It's just an experimental condition. If we would have measured at 0.01 or so, of course, G prime would have been lower than G double prime because there's a terminal zone. It's a typical liquid behavior. So we shouldn't make too much out of that, and shouldn't make too much out of the crossover of G prime, G double prime. 10 delta is more interesting. 10 delta in the sample which has been preheated to 100 degrees for a while. The whole structure had been melted completely. And then it's supercooled to 40 degrees. We look at crystallization and find the gel point where 10 delta is independent of frequency. And you see the frequency range is very large, in this case, much larger than in Klaas Teninhuis's experiments. 10 delta is amazingly linear over a wide frequency range. This is a real ideal behavior. We haven't seen anything nicer in a chemically complicated system. So in spite of all the differences between the physical and chemical gel, particle behavior is still very, very similar. I actually expected bigger differences between the systems because of the finite size of the crosslinks in the physically crosslinking system. If you have big crystals in that material, that should give us some filler effect or some additional changes in the network. And here it's a partially crystalline material. And still it behaves very, very much like a chemically cross-linking system. At 150 degrees, again, the same fingerprint. We know where the gel point is, exactly at the crossing of 10 delta here. So everything is fine until we take the sample, which only had been heated barely above its melting temperature. Melting temperature was a melting range, but about the average, the middle of that melting range was 65, and we only go to 75 degrees. It's a liquid behavior in the beginning, but then when solidifying, somehow 10 delta is not giving us one crossover. It must be a masking of two types of phenomena. It's not just gelation. There's maybe a phase separation coming in, or crystallization causes a phase separation in that structure because the crystalline region have purely isotactic sequences. Therefore, when you melt just barely above 65 degrees, you still will have a phase-separated region, and that type of morphology will interfere with the crystallization, and you get different behavior. And it's I think that's interesting. It's actually very nice to take a rheological experiment and use it as an indicator of some trouble in your sample. When you know there's a difficulty, you can use X-ray or DSC or other tools to look at details in the crystalline structure. And here we have some difficulties. It's even more pronounced when you look at 10 delta. Here I have 10 delta of that sample, and it's never flat. So you can see over in that frequency range, which corresponds to some size range in the material, there's some complicated morphology, and it needs some further analysis to describe what's happening. So one result of that study is that the thermal history affects the crystallization process, which it probably should. The wide frequency range of the power law is amazing. I was surprised to see that. It was very, very substantial, 4 decades in frequency. The network junctions are about permanent for crystalline materials. So we don't see any cutoff at low frequencies. And 10 delta is really very sensitive, is a sensitive indicator for the gelation process. We can see whether anything goes wrong. That is very nice for learning, learning about sample preparations. There are so many things which can go wrong. And just by measuring 10 delta, as time goes on, and you see your samples are getting better and better, that's a very nice tool. In fact, in the beginning, when we just started working with those systems, François Chambon took his precursor materials and cleaned them again. He went through one distillation after the other, and his experimental data, his results got better and better. So he claimed that a clean system gives a nicer network, and it probably does. It's getting your data are easier to analyze if you use a well-defined system. But the major improvement in his data really came through making more and more gels. So if he would not have distilled his materials, but would have prepared samples over the same period of time and would have done the experiments again and again, getting rid of all kinds of artifacts, his experiments would have been nearly as nice as the experiments with the highly cleaned samples. So the rheology is very helpful in developing the technique. A third sample, which I wanted to mention here, we'll move a little more quickly in this case, is a bacterial polyester. Has been derived by Bob Lenz and Fuller in the group here. The interesting part in this polyester is that it's biodegradable, so there's a lot of interest in this type of system. We got interested because it's a thermoplastic elastomer, which in the solid state has about 25% by weight crystalline component, So it's a rubbery material, and in this case, and it's really this property comes about because it's a copolymer having regions which can crystallize and regions which are amorphous. Walter Richtering got a sample here from Bob Lenz's group and measured, again, the melting. First, want to know what's the melting temperature of this sample. In the polypropylene, remember, there was 65 degrees. And in this polypropylene copolymer, if you take a pure isotactic polypropylene, it's about 165 degrees melting temperature. So the melting temperature is reduced by the copolymer character. So in this case also the melting temperature is fairly low. It's between 50 and 60 degrees C, as measured in a melting experiment at a frequency of 1. And in this case, the sample is softening gradually during this process. So the amplitude was 0.002, and it ranged up to 10%, or 0.1, when the sample was very soft. And those experiments have been published by Richtering, or the publication will appear very soon. In the liquid state, or also in the supercooled liquid state, so you could measure at low temperature. Here, everything is normalized to 20 degrees C. He measured G prime, G double prime, and you have typical liquid behavior for 10 delta. So again, quite normal for a material which is broadly distributed in molecular weight. Walter changed the degree of supercooling by crystallizing the sample now at different temperatures. 30 degrees, the highest temperature, is closest to the melting temperature of the system, so it will crystallize most slowly, and 20 and 15 degrees will give a faster crystallization. The preheating temperature was high enough. We picked a high temperature much beyond TM, so there was no effect really of the thermal history. Everything was melted out. So at different supercooling temperatures, here at lowest, the deepest quench, lowest temperature of crystallization, crystallization occurs very fast, a little more slowly, and slowest at 30 degrees C. If you have a slow crystallization process at high temperature, you most likely get higher order crystals and different crystal sizes also. So the crystallization will depend on the choice of that temperature. For crystallization at 20 degrees C, the tan delta again decayed as expected in our experiments. Now omega wasn't changed over such a wide frequency range. It's 30. But again, we can use tan delta, put a tangent to those curves, and then get the gel point directly. You can see a very nice evolution in the liquid state, but then in the solid state, some more things are happening probably as we move further beyond the gel point. Maybe the crystal lamellae or whatever interesting morphology is coming in. Tan delta first G prime, G double prime at the gel point is given by the typical power law behavior. This is the liquid state before, this is at the gel point, and then it moves up further when cross-linking beyond that, and tan delta is flat at the gel point. Yeah, this is the typical fingerprint of the material at the gel point, before the gel point and after the gel point. So again, we can use the rheological experiment to determine the behavior in the vicinity of the gel point. We can do that here because crystallization, again, is very, very slow. Similar things occur when you quench even deeper, go to 15 degrees C, everything occurs faster. But it is the same type of evolution. And again, we know the time of, we know where the gel point is. Now that's interesting to know. When you're working with samples like that, and somebody tells you, when you supercool to 15 degrees, you have a gel point at maybe 9,000 seconds. That's helpful for designing your experiments, and it's easy to get. It's easy to get it this way. I don't know any other method which gives such a gives the result that directly and that handy. Interesting is the crystallization at higher temperatures. We look at 10 delta when crystallizing at 30 degrees C and find that there's no single crossover time. So somehow, again, when we are closer to the melting temperature, in this case we are closer to melting temperature during the crystallization process, something else happens. Maybe the crystal sizes are in the order of the sample size, or something odd is happening, and we don't know what is happening. When you look at DSC, crystallizing the sample for 24 hours at 20 degrees, 30 degrees, and 35 degrees now, the melting transition moves to higher temperatures. You're somehow producing crystals of higher order in this case, so you would expect a higher melting temperature. But also those crystals have been produced, and then during the DSC you're melting that crystal basically. So you're looking at the melting process in this case. So the general structure of the melting process is different when crystallizing at different temperatures. It seems to be a high sensitivity to the degree of supercooling. Then there's a nucleation and growth process which probably follows different evolutions. And in the DSC you couldn't conclude that very easily. But combining this with the rheology, you know there's something interesting happening, and in Bob Lenz's group, they're now looking at details of the crystallization process, and then when we combine rheology with the morphology, we learn about something interesting. So that, I think, is a general trend in rheology, that you will be combining the rheological experiments with all kinds of other physical experimental methods, and then get a more complete picture. Now, this is all I wanted to present about gels and about networks in general. I brought material on polymer blends, but I'm not sure whether there are only 10 minutes left, whether we should be starting a new subject. Well, maybe I should start introducing or explaining a little bit about polymer blends, about a blend sample, since I mentioned polymer blends before as a material which undergoes power law relaxation. And I could go back to this experiment and talk about this a little bit. See, it's a transition which we are interested. We want to see what does the phase transition to the rheology. And we picked a model system which has an accessible phase transition. And we will do rheology in the one-phase state and rheology in the two-phase state, and see whether rheology undergoes an interesting evolution. The system which we used consisted of polystyrene, fairly broadly distributed, because the partner, the second polymer, which we were using, the polyvinyl methyl ether, is not available in our distribution. Ideally, we would like to have both components of very narrow molecular weight. But here, they are fairly narrow, but not perfect in that sense. The polystyrene has a side group which is interacting with the side group of the polyvinyl methyl ether, and due to this interaction, a single phase behavior is probably seen in this material. The data which I will be showing are from Suresh Mani's experiments, which are published in Macromolecules in '91, and there are 2 more papers coming out from his experiments. The phase behavior is characterized by a phase transition at about 110 degrees. If you go beyond 110, the sample is two-phase, and below 110, it's a single phase. If you go to even lower temperatures, the material undergoes a glass transition temperature. This is 0 degrees, so the glass transition temperature is fairly low for most of the samples. However, if you go into the two-phase region, if you quench and go to a higher temperature, quenching is normally associated with going to a low temperature, but let's call this also quenching because we are moving into a region where we are phase separating, going deep into that, and then you separate this material into two components, and one component will be very rich in polystyrene, and that will have a very high glass transition temperature. So after phase separation, one component will be very stiff in its behavior, and the other component will be rich in polyvinyl methyl ether, will be very mobile. So the rheology is very asymmetric in this case. The rheology of the individual components is typical for for broadly distributed polymers of high molecular weight. Here we have 80,000 molecular weight for PVME, G prime, G double prime. The material is very, very soft due to the low glass transition temperature of about minus 30 degrees C. All our blends are studied in the vicinity of 110 degrees C. So we extrapolated the data which were measured at 25, 50, and 70 degrees, and we determined shift factors in this case. Now we extrapolated those to a new reference temperature at 110. Because in the rheology, we will decompose our system into components, and we would like to know what's the rheology of the components at that temperature. So we really would like to know the PVME rheology at 110 degrees, which is characterized by very low values of fairly high cutoff longest relaxation time. And we also took data on the polystyrene at temperatures much above the glass transition temperatures. 145 degrees was the highest temperature. But again, from those temperatures, we determined the shift factor and shifted everything to 110 degrees C. So it's an extrapolation. I know that we are introducing an error when doing that, but it gives us an order of magnitude feeling about the relative mobility of our two molecules. And when you compare that mobility, take the cutoff time for the PVME and the cutoff time for the polystyrene, then you find, then reading down here the omegas, that there are about 10 orders in magnitude difference between the cutoff time, between the longest relaxation time of the two components. So the PVME is very mobile, polystyrene is not very mobile, because at 110 degrees the polystyrene is very close to glass transition temperature. So these are the typical spectra which we are getting. Now the spectrum of the blend, say of a 60% polystyrene, 40% polystyrene, 60% PVME, has a broad transition from the terminal zone to the glass. That's like a really broadly distributed polymer. It's very typical for that. And again, this is being shifted to 110 degrees. In this case, we actually have some data at 110 degrees, but data have been taken at temperatures below. All data were taken in the single phase region. So this is without phase separation, what you're seeing here. We are moving up to the coexistence temperature, which is close to 110 degrees C. Now, the shift factor has been determined in those cases here for high temperatures for the polystyrene and low temperatures for the PVME and for the blend. Somehow the blend and the PVME have very similar shift factors, 80. So we are using this shift factor and extrapolating up here to get the relative shifting of the systems. For performing rheology, we are quenching the sample. So we start at 90 degrees, where the material is one phase. We go to the two phase. It decomposes into the two component, the polystyrene-rich, PVME-rich component, and both of them are very asymmetric. It needs a while for the structure to develop. So after quenching here, one has to stay with the sample and wait till a stable rheological response has developed. This response is given here, the modulus, as a function of time, modulus doesn't change very much at lower temperatures. But then when moving beyond the coexistence temperature, there's an evolution of G prime, G double prime. But it levels off after about 100 minutes. There's still some changes going on, some very, very slow changes in the morphology. The coarsening of the structure needs a very, very long time. But after having waited for those 100 minutes, we perform rheological experiment, G prime, G double prime. Before that, there would be an extreme change of G prime, G double prime, and we couldn't associate a spectrum to a single morphology. And by doing that, you might remember the phase-separated system here has the power law coming in. That's what we discussed before with the gels when we talked about other systems with power laws. And this is the liquid behavior, which you saw before. For the liquid behavior, we have a broader, more extensive curve, but everything seems to be happening at very low frequencies. At high frequencies, the spectrum is not affected. Only the long times, the large-scale mobility is affected by the phase separation. It's slowed down by the phase transition coming in, by the interface coming in. And that's really what we would be expecting. At different composition, this is at a lower polystyrene composition. It's the same general evolution. Only at low frequencies we see something. At higher frequencies, the phase transition is not visible. So if you would perform dynamic mechanical experiments at a rate which is too high, you would not detect any phase transition in rheology. Your conclusion would be that rheology is insensitive to phase transition, while light scattering or some other technique which gives you the divergence of some large fluctuations would be sensitive. And the answer to that question, or the response to that suggestion, would be look at the behavior over the whole frequency range and then see whether the response, the molecular mobility, is affected at certain frequencies, in this case at low frequencies, and at others if it's not affected. So rheology is an interesting tool to monitor phase transition, but it might fail if you have incomplete information. Next time I will combine rheology with another technique with fluorescence quenching, a technique which measures phase transition on a 20 angstrom level. And with fluorescence, we know exactly where the phase transition occurs. And then we have to look at all kinds of rheological responses and see where rheology is sensitive and where it isn't. So we will look at this type of combination. Thank you. This is it. Monday is Easter Monday, so I don't think we will have a class. Is Tuesday Monday, or is it vacation? Or Wednesday is Monday. In Massachusetts, it's always changed. Yeah. I suggest the next time they should make Friday Monday in Massachusetts. Yes. Or make Sunday Monday.